At 1,667 feet, the ground is turning to liquid. Why hasn't this billion-dollar tower snapped? The answer is hidden in the golden sphere. What happens when the Earth itself decides to move? Inside a skyscraper, the world can become a terrifying place. The floor begins to shift, a subtle, disorienting roll that grows into a palpable sway. Glasses tremble on tables, their contents sloshing over rims. People instinctively reach for solid objects, for desks, for door frames, trying to anchor themselves against the building's slow, rhythmic dance. Outside, the city may be in chaos, sirens wailing through the concrete canyons. But high above the streets, the tower is fighting its own battle. It is a battle it cannot lose, and it does not break. The reason for this resilience is not immediately obvious. It is not found in the foundation deep within the earth, nor in the gleaming facade that greets the sky. The secret is hidden away, suspended in a vast chamber near the top. It is a colossal golden sphere, a massive, silent orb hanging in the gloom. To the uninitiated, a frightening sight. A giant pendulum with deliberate grace. It moves in opposition to the building's fear. This unseen guardian is what calms the storm. It is the steady hand that soothes the trembling giant. Skyscrapers, by their nature, must be flexible. They are not rigid monoliths, but engineered to bend. If perfectly stiff, wind and quakes would find no release. Stress would concentrate, fracture would follow. So engineers build in a degree of sway. But flexibility creates its own problems. Too much motion makes people sick. It can crack partitions, shatter glass. The challenge is not just allowing movement, but controlling it. Let the building yield, only to a point. Dampen the sway. Bleed energy before oscillations grow. A delicate balance between rigidity and flexibility. In Taipei 101, that balance comes from mass and motion. The tower moves, but its protector moves more wisely, so the dance never becomes a disaster. This colossal swinging orb has a name. It is a tuned mass damper, or TMD. Housed between the 87th and 92nd floors of Taipei 101, it is the largest and most famous of its kind. The sphere is comprised of 41 layers of solid steel plates, each precisely welded into a perfect globe, measuring 5.5 meters across. Its total weight is 660 metric tons, more than 100 adult elephants. This is not arbitrary. Mass resists changes in motion. In a battle with nature, you need a lot of it. It is suspended by 8 thick steel cables, each a braid of smaller wires for strength and flexibility. Below, a steel ring acts as a bumper, limiting swing to 1.5 meters in any direction, preventing any strike on the primary frame. Anchored beneath are 8 enormous hydraulic cylinders. These viscous dampers are the system's shock absorbers, dissipating the energy the pendulum absorbs. The term is precise. The mass provides inertia. The damper turns motion into heat, but the most critical word is tuned. Its natural frequency is matched to the tower's. That tuning is the key. A gust pushes right. The sphere swings left, then right as the tower returns. Out-of-phase motion creates counterforce, pulling the building's motion down. A simple concept, executed on a monumental scale. People look small beside the giant, a reminder of the forces it commands. Imagine 2 identical towers side by side. A powerful invisible force, wind, pushes. Split screen, left versus right. Without a TMD, sway becomes dramatic. Inside, objects slide. Stress flashes in angry reds. Now look right. It contains a TMD. Same wind, less sway. A large mass near the top moves in the opposite direction. Tower right, mass left, tower left, mass right. Perfectly out of phase. Counterforce pulls against wind. Occupants feel only a minor tremor. Think of it as anti-lock brakes for a skyscraper. It handles inertia, so the structure doesn't have to. The swinging mass is only half the solution. As it swings, it drives pistons within the dampers. Thick oil is forced through small orifices and valves, creating immense internal friction. Kinetic energy becomes heat, which slowly dissipates into the air. The TMD drains energy. Oscillations die faster. Energy spikes are absorbed and flattened, protecting steel bones. A 660-ton steel sphere cannot be built on the ground and simply lifted into place 90 stories up. No crane is large enough. No opening is wide enough for a finished sphere. It had to be constructed in situ, assembled piece by piece within its chamber. Like building a ship in a bottle. Only the ship is a million-pound ball of steel, a feat of logistics and engineering. Plates arrived as puzzle pieces, lifted by compact cranes inside the core. From the bottom up, curvature by curvature, every weld ultrasonically tested. Precision was immense, the final sphere perfectly balanced. As it formed, other systems closed in. Suspension cables were lowered and readied, dampers were bolted to concrete below. A slow, deliberate dance of iron and skill. Steel rang through the tower's skeleton, a factory in the sky, forging its heart. Once the shell was complete, critical connections were made. Weight transferred carefully to 8 cables, each tensioned to its share, every bolt to exact torque, every connection double-checked. A pendulum of immense power, forged in the heart of the skyscraper. Before activation, it had to be proven. Prototypes endured punishing trials, millions of cycles in weeks. Drop tests simulated shock loads. Oil temperatures verified for typhoon and quake energy. Commissioning inside the tower. Controlled trial runs. Response measured through a sensor network. Strain on cables. Acceleration on the mass. Data matched the models. Controls fine-tuned. Then, constant vigilance. Regular inspections. Welds. Tensions. Seals. Oil sampled and analyzed. In 2015, Typhoon Pseudolore hit with 100+ mph winds. The damper swung a full meter, reducing motion by up to 40%. The Golden Sphere of Taipei 101 is the most famous tuned mass damper, but it is far from the only one. Type depends on height, shape, and forces. Some use massive sliding blocks on controlled tracks. Pendulum, sliding mass, slosh tank. A slosh tank uses tuned water motion as the mass, timed to the building's natural frequency. Others deploy dozens or hundreds of smaller dampers, working in concert to tame floor vibrations. Beyond buildings, chimneys, bridges, grandstand roofs. Even race cars used small mass dampers. Banned later, but the idea proved versatile. In the end, the 660-ton sphere is more than remarkable engineering. It is foresight and a symbol of safety, a silent sentinel waiting for wind or quake. Its concept is simple: use weight to fight movement. Its execution, metallurgy, hydraulics, control theory. It converts violence into harmless heat. It moves, so the building doesn't have to as much. It absorbs the chaos. Hidden engineering makes the vertical world possible. You trust calculations, welds, and relentless testing every time you rise into the clouds. Think of the massive pendulums, the sliding blocks, the sloshing tanks, the silent partners in our reach for the sky. Hidden engineering is the only reason the tallest buildings stand. Next time you're on the 90th floor, remember the golden giant keeping you safe.